Okay, good morning everyone. Let's start this module of steel design, which is the advanced steel design to S4100 combined actions. Okay. Now, if I ask you what we have done before, what we have done before is we have understood or we have learned how a member is subjected to different kind of forces. For example, tension, compression, bending individually, isn't it? Individually, we have studied that if a member is subjected to individual forces, how can we analyze them, right? Now, in this case, we will be looking at combined actions. Combined actions means suppose your bending and compression force is acting together, or tension bending, or there is a bending about both principal planes. And you will find in reality, most of the time, the scenario will be like that. That means that all the forces you will find, or most of the time, forces will act simultaneously. That means we have to look for members, look for how we can analyze the members when they are subjected to combined actions. Okay, now let's look at this interaction effects, how this interaction effects works. Now I will start with the second one and then we'll come to the first one. There's a reason for that. I'll explain that in a minute. So if you look at the second one, what we are saying is when we have the axial compressive force and bending both are acting, that means you have a compressive force and then we have a bending. Then what happens is axial compressive force reduces the bending moment capacity of the beam column. Why we are using the terminology beam column? Because you see it's a column which is subjected to axial load, but it is also subjected to bending. So that's why we are talking about this thing, that yes, this is also, and this is also can be called a beam. So we will call it as a beam column. Now it is obvious that the axial compressive force will reduce the bending moment capacity of the beam column. Why is it obvious? Because you see, when you have a bending, right, then we have a compressive force acting. And so some imagine this way, that a portion of the cross section will be taking, or some of the compression resistance will be taken away by the axial compressive force, and the some part will be taken by bending. That means essentially they will be shared. That means automatically this will reduce the axial compressive capacity. Understood? That means what I'm saying is, you can think of when you have the interaction effects, you have a pie chart like this. Suppose you have this circle, right? Now, if you have three interactions, means you see, three will share these compartments. Yeah, if there are two, there can be two. And that, see, the compressive capacity cannot exceed a certain value. So if you want to share it between different loads, automatically what will happen is that the other capacity will be reduced. Say you have used 30% for axial, 30% for tension, for example. It is maybe an hypothetical example. In that case, there is only 40% left for bending. So that's the general thinking behind it. And when you have the biaxial bending, again, you have the similar problem. So the axial member and the bending capacity both will be reduced when you have the biaxial bending, because in this case, as I've said, that all the capacity will be shared by, say, compression, bending, etc. Now let's look at the first one. First one, we are saying column buckling and bending interaction amplifies bending, and this is called the second order effect. What do you mean by that? Second order effect. Let's think of suppose this beam is under bending, but it is also subjected to a compressive force. Now this is like this. Okay. Now what will happen is This will not be obvious unless this member is very close to the buckling capacity. This is very important, or close to the buckling load. I mean the axial load. So let's put it this way. If that load reaches very close to the buckling load, what will happen is this deflection, which is due to the bending, will be amplified. And this can be amplified severely. Okay. And that means in this case, that axial force will actually amplify its bending severely. But in general case, if you think of, still, if there is a small deflection, this axial force will produce a bending moment. That means it will amplify the bending. So you cannot solve the problem just using your first order effect. That's why it is called second order effect, because if you write the differential equation of this, then you will find that the differential equation is a coupled differential equation. Okay. And this coupled differential equation, so let's look at it this. I can actually show you here. So if you cut a section and then draw the shear force and bending moment, you will actually find that if you write this, whatever this square y dx square equals whatever, the one will be the m, which is the effect of the bending. That means you have a reaction, then you have Rx minus Wx square divided by 2. And then you have another component. Say this is your M moment. So then you have another component which is due to the axial force. So that means that will also produce a moment. So if you look at the sine component here, so this will produce the same directional moment, which is your axial force. So it will be minus P, if that P is a compressive force or axial force, P times X. So you see that this P times X is the additional moment which is produced due to this axial load. And this is called the second order effect. So what is the bottom line, or what is the summary of this item? It says that yes, if we have buckling and bending both occur together, then of course there will be an interaction which amplifies bending, and this is called a second order effect. Second order effect means you cannot just solve the problem using the first order. That means you cannot use superposition. Let's look at it this way. For solving such a problem, you cannot just use you cannot just say, okay, one part is due to the load and another part is due to the axial load. No, you have to solve the problem in a combined way, and that's why it is called second order effect. Any question about this? So the first order effect which we have done so far, that means the first order effect is basically, when you are doing something and you can use the superposition. That means you are analyzing separately and putting them together, which is your method of superposition. But when you look at this kind of second order effect, that means you are combining buckling and bending. Now let's continue. Now the bending moment plus axial load we'll be looking at. Now in this case, hello? Okay. So the bending moment plus axial loads, which is the reference is section 8 of AS4100. Now you see there's again a change in section. So follow this one. The section 8 of AS4100 you'll be using. Now, what is the prerequisite? This is the important one. Always look at the prerequisites. Can I request all the people, please mute your microphone. So the prerequisite is, this is very important. So what's the prerequisite here? Section must be okay as a beam. You see that if the section itself is not safe for carrying the bending moment, then there is no point to consider it to carry an additional load. So section must okay for as a beam for moment. Section must be okay as a tie or strut for an axial load. That means when these loads are acting separately or applied separately, the section must be okay to carry them. If the section fails, then there is no point in moving forward. So think of this section 8 is which talks about this interaction effect. Modes of failure: local yield and or buckling controls section capacity. So the local yield and buckling, yes, it controls section capacity, which you already know, isn't it? Which you already know from our previous study. Now we also know that yes, it is the overall buckling as a beam or column that controls the member capacity. You see, this is very important, which controls the member capacity, overall buckling. So these two are distinctly different. I'm highlighting because these statements are different. Need to prevent all possible modes of failure. Very important. So if you do not prevent all possible modes of failure, as I always say, that nature follows its own way. That means nature will follow the weakest link and will cause the failure, and it will not tell you. So it is our job to understand that yes, these are the possible modes of failure and we have to prevent them. Now, verifying the capacity of members under excuse me, combined actions. Check the section capacities first. As I've said, if it fails in section capacity, no point in moving further. Then you check member capacities. Now the new thing is, excuse me, coming into the equation, check the biaxial bending interaction. That means if you have a biaxial bending, then we have to check the interaction. Now we'll come into that in a minute, how we can check that. But this is the new thing when you have simultaneously different loads are acting. Now the member behavior under combined actions, first we are thinking of in plane, where the load and buckling deformations occur in the same plane. This is how is it possible? Imagine that that a beam is bending about x-axis, which is your major axis, and the buckling is also happening about the major axis. That's why that means both the bending deformation and the buckling deformation is occurring in the same plane. But remember, this can only possible if you block the outer plane. That means there is no possibility of buckling in outer plane. Now next we'll look at outer plane. Load and buckling deformation do not occur in the same plane. Bending about the major axis but buckling about the minor axis. And you see, this is the reality. In reality, most of the cases things will be like this. So imagine if you have this beam like this and then it is bending like that. Yeah. Suppose you have it is subjected to a compressive force, a compressive load. Then what will happen is it will buckle about the minor axis. It will bend about the major axis and it will buckle about the minor axis. That means, and that's why it is called out of plane buckling. So this is the scenario where bending is about the major axis, but buckling is about the minor axis. And then we have the biaxial bending, where we have the bending about both principal axes. So that means you can have a biaxial bending. Now some examples of those. This is an in-plane capacity example. So buckles in the same plane as the moment, which we have just talked about before. So moment about y axis, but it is bending about x axis. Correct? So in this case, what is going to happen is that because we have a resistance, imagine there is some imaginary resistance for the member not to buckle about the in the outer plane. So both buckling and the bending will occur in the same plane. Okay. So see this figure now. So then it will be clearer. So you can see that basically this is now buckles in the same plane as the moment. Okay, so buckles about x-x axis in y-y plane. If you get confused, think this bit by bit, because this is a slightly newer one which you have studied from what you have studied before. So think carefully. In this case, you are talking about both bending deformation and buckling deformation are occurring in the same plane. And that's why we are talking about the word in plane. And in this case, of course, there's a resistance about buckling, about the for buckling about the y-y axis. Now let's look at the out of plane capacity. In this case, you see buckles about y-y axis in x-x plane, but moment is about x-x axis. So it is bending about the major axis x-x, but buckling about y-y axis, that the weakest or the minor axis. Can you see that? Yes. So it's bending about this axis, bending is like that, and you have the buckles. It is actually buckling in a different axis. Okay, so that's why this is called out of plane buckling. Now let's look at the interaction diagram. That's a very interesting one. Now, what does the interaction diagram means? That is the same pie chart which we were talking about before. That means your capacity maximum is this within this circle. So whichever way you divide, you cannot exceed the area of the circle. Same thing is here. What we are saying is, suppose the capacity is divided between the axial force and the bending moment, like axial compressive force and my major axis bending in this case as shown, then the capacity of these two, that means if you write this plus, now again X stands for the major axis and star stands for the factor load. That must be less than equals 1. So you see that because this is a proportionate one, so that's why the summation is 1. Proportionate means if you think that moment is taking the 2/3, then this axial force maximum can have 1/3, like that. And this is represented by this plot. You see, this is the limit 1.0. And within this zone is safe. That means if the summation is less than 1, then it is always safe. But when the summation exceeds 0, this is unsafe region. That means this is going to fail. So this is called the interaction diagram. So there are two ways of checking it. Yes, if you have a plot, one can use the plot to check it, or you can use this expression to check these things. So you can see the same thing, the interaction formula which I have just shown you. So this diagram represents the section capacity formula for uniaxial bending about x-axis. Now, one thing I'll tell you here, please read the terms very carefully. We are talking about section capacity here, very clear. So first we are looking at section capacity, because what you have said, if section capacity fails, then no point in going further. So first look at the section capacity formula. Then what we are also saying, uniaxial bending about x-axis in clause 8.3.2. Uniaxial bending about x-axis, that is the interaction formula which we have just shown in the previous slide. Now if you rearranged, then you get this one. Rearrange means then what does it mean? That means if you know n star, or if you know what is the compressive force or compression capacity and the moment capacity, then this formula will tell you that is the maximum moment this section can carry. That's what the formula is. Other combined actions formula similar. And in this case, we have MSX is the nominal section moment capacity about x-axis. Yes, obvious. NS is the nominal section load capacity, clause 6.2 for axial compression and clause 7.2 for axial tension. And N star is the applied compression force. You already know that. That's N star, factored compression loading. So if you consider uniaxial bending about the x-axis, this expression is this. Mx star over 5 times MSX plus N over phi times nx less than equals 1. Now, similarly, when you consider uniaxial bending about the y-axis, then the expression is like that. Can you see that these expressions are actually similar? Only the change what has happened is that instead of x, we have written y here. And you can see in this case, yeah, both bending and buckling will happen in the same plane. Yeah, okay, we are not talking about this here, only section capacity, but it's good to think that we are just talking about the section capacity here, but I am telling in addition, in this case, both will happen in the same plane. Then we are coming into the biaxial bending. Biaxial bending means you can think of some sort of superposition thing we are doing here. So bending about x-axis, bending about y-axis, and then you have this axial compressive force. So mx star over phi times msx plus my star over phi times msy plus n star over phi ns. And you can see always the summation is less than equals 1. This is the main thing. Because as I've said, because we are expressing this in terms of a proportion, you can see this is a ratio. This is a proportion. So their summation always will be less than 1. Okay. Any question up to this? This is a section capacity we are looking at. No question? Okay, we will now move on. Now let's look at the member capacity now. So you see that we are doing one by one. First we are looking at, we have looked at the section capacity. Next we are looking at the member capacity. What we are saying is the sign of the axial force is important. Why is it? Because the axial tension helps to prevent the lateral buckling. Because if you pull a member, automatically it will help you to prevent the lateral buckling, which is good. On the other hand, axial compression has the opposite effect. That means it can actually, in fact, increase the deformation. Yeah, so that's the problem. Now the member capacity in tension, the in-plane capacity for tension members is the same as the section capacity. Important statement, in-plane capacity for tension members is the same as the section capacity. Correct? So that is understood. Now outer plane capacity for tension members will be given by this. Now, when you are, okay, let's now think in that way. We are looking at a member which is subjected to tension as well as bending. Then we are interested in calculating the outer plane capacity for such a member. Then your mx star, which is the maximum moment it can carry, is given by this, where mbx is the nominal member moment capacity of the member without full lateral restraint and bent about major principal axis. Now this is an, so can you see what we are doing here? Because we are looking at out of plane capacity instead of the msx, that's the section capacity, we are now using mbx. So step by step, first ensure it is safe in section capacity. Next we are going into member capacity. Now when it comes to member capacity, you see out of plane capacity means we have to consider mbx. Yeah, if you recall from bending. And then we have this n star and nt. And phi is the capacity factor, and then this expression will tell. So if you solve this one, it will tell you the value of the applied bending moment, yeah, which you can safely apply. That means you have to solve this inequality. Okay, now just hold on. What I suggest you to do is to look at these clauses in parallel, because in that case, you get a bit of, feel for it. So if we look at the section 8, it first starts with the section capacity, and then it looks for the member capacity, which we are looking at now. Now, when we have the tension capacity, this is what we have shown. Here in this expression. And then we are looking at uniaxial bending about the x-axis and calculate the in-plane and out-of-plane capacity. What is the change now? It is compression. Now you see how the expression changes. For the in-plane capacity, all this is section capacity, this is your section capacity. You see NCX is the section capacity. So, sorry, NMSX is the section capacity, but NCX is the nominal member capacity. Why member capacity? Because you see, imagine this scenario. This is bending in the same plane and buckling in the same plane. Then of course we have to go for the member capacity for buckling, compression, compressive force. But section capacity first will go. First we'll check whether it is safe in the in-plane capacity or the section capacity, and then we'll go to the out-of-plane capacity. So in order to understand this carefully, let's look at it this way. Don't get confused with that. In this case, in-plane means both are happening in the same plane. You can see that means about x-axis. That's why x is appearing here. Am I right? Think carefully about this. If you look at this expression, which we are talking about now, it is bending about x-axis. So that's the section capacity ratio. And if you look at the second term, that actually gives you the possibility of buckling about the same axis. That's why we in plane. And in this case, NCX is the nominal member capacity in axial compression for buckling about the same principal axis, which is obvious because that will limit the capacity. But when it becomes out of plane, things become different. Then you see MSX becomes MBX. Because now we are allowing out of plane means a member capacity of the bending we have to consider because it can limit the out of plane bending or the bending capacity. So MBX, the nominal member moment capacity determined in accordance to clause 5.6, which you have already come across. And then you see, because there is a possibility of out of plane, though the beam is bending in about x-axis, buckling will be about the minor and that is y axis. That's why NCY. Can you see the change now from this expression? Because this is when we are considering out of plane, we are considering the worst case scenario. So now you consider the nominal member capacity in axial compression for buckling about the minor principal axis, that is y-axis. Any question about this? This is an important one. So when we have the compression and bending, first we are checking for the in-plane capacity and then we are going for the out-of-plane capacity. See, look at it this way. If your in-plane capacity fails, then your out-of-plane capacity will obviously fail because you see, once you allow out-of-plane, then all these capacities will be reduced. Okay. Now, if you consider biaxial bending, then it is mx star over phi mcx, where mcx is the lesser of the nominal in-plane member moment capacity and the nominal out-of-plane member moment capacity for bending about the major principal axis. That's an interesting one. So what is MCX here? We calculate two capacities, nominal in-plane member moment capacity MIX and the nominal out-of-plane member moment capacity MOX, and then get the lesser of these two. Remember, we are talking about major principal x-axis bending. But in this case, still if you allow out of plane, there could be lateral torsional buckling and that can reduce the moment capacity. And that's what we are calculating MOX. So MIX, you calculate MIX, MOX, take the lesser of these two and it is sorted. And what is MIY? The nominal in-plane member moment capacity for bending about the minor principal y-axis, because in this case, there is a moment which is acting about the minor principal axis. So that's your MIY. So you see how we are calculating MIY. It is based on MSY is of course there, understood, and then you have NCY. So in this case, we are considering that yes, there is an axial force acting. If there is an axial force acting in star, and then we calculate the member capacity, and that limits your nominal in plane member moment capacity. Okay, so this is the case for biaxial bending, because you see that always there is a possibility of buckling about the minor axis, and which limits the capacity of that member when bending about the minor principal axis. This is a bit involved one. So please, what I suggest, you can actually note these things down. Note means you take step by step, like, section capacity subjected to compression and bending. What is the scenario? Tension, bending, what is the scenario? Bending about both the axis, what is the scenario? First you go to the section, then you go to the in plane, then you go to out of plane. Yeah. So there's a step by step. I'll repeat. First section capacity, then you go to in plane, and then you go to out of plane. And then there are three different scenarios we are looking at: tension and bending, compression and bending, and biaxial bending. So the basic design procedure: analyze structure for moments and axial loads in member, include any second order effect. That is only, as I've said, when you have this bending and buckling. Yes, we can have some of the cases the second order effects. Then you have to include that. Check all sections for section capacity. Very important, using clause 8.3. In practice, the most heavily loaded section usually where the moment is largest. This is obvious. Check member capacity using clause 8.4. Use maximum values along member. Watch the sign of the axial loads, tension or compression, as compression reduces a member section capacity and member capacity. See, the compression is a problem. But on the other hand, tension reduces a member section capacity, of course, but increases its out of plane bending buckling capacity, because it pulls buckled member back straight. So that's the advantage. Now AS4100 gives two sets of interaction formula. One is for general use and other for doubly symmetric sections that meet certain criteria. That means compact section. If you recall, compact section means such sections where if you increase the load, it can go to up to full plastic capacity. That's why they are called compact sections. So if you generally think of a general symmetrical I section, will be a compact section, doubly symmetric one. Now tests show that compact doubly symmetric sections perform better, 15 to 20%. You may use whichever formula applicable, but the basic principles still apply. That means you can use either of the formula, but your basic principle remains same. Any question before we go to the example? Very good. So all good. So we'll look into the work example. All examples use 200 universal column, 52.2, which you are familiar with. So 200 millimeter is the depth of the section, and its self weight is 52.2 kg per meter. Grade 300. Effective lengths LEX and LEY are 4 meter. So we are using only the general formula. And you see we have LEX and we have provided these two, otherwise we have to calculate them. See, very important. For compression, if only length is given, then you have to calculate the effective lengths. Example A, so N star is 750 kilonewton compression and M star X is 60 kilonewton meter. So we have to analyze this scenario where a member is subjected to these two loads. compression, and bending about x-axis, bending moment about x-axis. Buckling about y-axis is prevented. You see the interesting point here? That's what I'm saying. You have to be clear about what is the scenario here. So no buckling about y-axis. Let's proceed. Buckling about y prevented. Let's calculate the section capacity about x-axis, which is MSX, is given by Fy times ZDX. Fy is 300 MPa from one steel table. Okay, yeah, so whatever section you have chosen, yes, we can look into the Fy. And remember, when you are considering bending, then we use always the flange properties. We talked about this before. The flange Fy yield stress will be used when you are using the section the bending section capacity. And when you are using for shear, then you use the web capacity, because it is the logic is simple, that major bending load will be carried by the flanges. So Fy times ZDX, this is Fy and this is your ZDX, which is given by which is this. And then you have NS, which is Kf times An times Fy. This is the section capacity under compression. Kf, which is the form factor, times net area times Fy. Nothing is provided, so we can take net area as the gross cross-sectional area. So say 1998 kilonewton. So you see, first we are interested, or first step is to calculate the section capacity, because that's if you don't know that, then you cannot go any further. Now we are calculating the lambda nx. See, there's no buckling about yy, so let's consider buckling about xx axis. So buckling about xx buckling we are considering. So in this case, this is in plane behavior, right? In plane capacity we are looking at, because both buckling and bending are happening in the same plane, correct? So lambda nx LE over R times square root of kf times square root of this one is 49.2. Okay, that's so lambda nx. Alpha b equals 0 from table 6.3.31, and alpha cx is 0.861. So that's from the table. You are already familiar with this procedure. We are interested in calculating what is called the slenderness reduction factor, which is your alpha cx. And once you have got alpha cx, which is a function of alpha b and lambda nx, yeah, then we calculate the ncx, which is the member capacity, which is alpha cx times nx. We have already had the section capacity, so use this value here, and you can see there's a reduction there because of the possibility of buckling. So that's the member capacity, 1720 kilonewton. That means whenever, though both are happening in the same plane, but in compression, what is going to happen is, in the compression, it is a member capacity which is the limiting one, yeah, and that will govern the behavior in compression. So NCX is given now 1720 kilonewton, and you can see we are checking two things. First, we are checking the section capacity. As I've said, if it fails, no point in going further. So it is less than 1, that is safe. Now we are checking at the member capacity. Now, when you are checking the member capacity, the two interesting things you know. What are the changes here if you compare, say this is equation 1 and this is equation 2. What are the differences? You see this one now is become the member capacity in bending. But in this case, you can see section and member are the same. Why? Because there is no out of plane buckling possibility. So both capacity is the same. But when it comes to a compression, it is a very different scenario. For the compression, section capacity and the member capacity, even considering buckling about x-axis is different. So that's why these two values are not the same. This is the section capacity, that's the member capacity. That's why these two values, then these two are different. Again, you get 0.87 less than 1, which is okay. So the section is satisfactory. And if any of the check fails, as I've said, if the first one fails, revise the whole section. If the second one fails also, again revise the whole section. So two steps we have followed in section capacity, then member capacity, but in this case both were in plane. Now let's expand further. Now, if you think, okay, in the previous one, we have said that buckling about y-axis is prevented. That's a minor axis. Now, if you say, okay, no, the section can buckling about any axis. So in that case, we want to ensure whether we have enough restraint to prevent y-axis buckling, because that's the major one. If you allow buckling about any axis, means it will buckling about the weakest axis, and that's your minor axis, means y axis. Check the out of plane capacity. Assemble the values mbx is given by alpha m times alpha s times msx. In the absence of further detail, take alpha m equals 1. As I've said, this is very conservative. If your bending moment, if you know the bending moment, use table 5.6.1 because that gives you much accurate value. This is a conservative one, alpha m equals 1. In this case, there is no details available, so you can do that. That's fine. And then we are calculating MOX with MOA, which is your reference buckling moment, using this expression. Now, if you recall, this expression basically gives us, if there's a possibility of the lateral torsional buckling, what will be the buckling or the reference buckling moment, the capacity of the section. And that's why that is given by this one. Now, one can do an elastic analysis, or one can use this formula, which is given in the standard. So MOA is your M0. Now, this expression, if you recall, it is in section 5. So we can even, if you want to write, you can write this one. This expression is given by, just hold on. This is your given from section 5.6.1. So this is a very important clause actually. Section 5.6 segments fully or partially restrained at both ends. So look at section 5.6. So you calculate this MOA or MO, the reference buckling moment, with IY, that's all, or IW, that's a warping constant, J, which is the polar moment of inertia. You already know J, right? IX plus IY. We all get it from one steel table. So you don't have to calculate them unless you have a built-up section. Then you have to calculate all of them. So then you calculate alpha S, which is your slenderness ratio, or not the slenderness factor. If you just hold on again, we are looking into the particular section of the thing for this one. So if you look at alpha m, which I've already talked about, the moment modification factor, and alpha s, which is the slenderness reduction factor. See, why I'm looking into this, because you see there are two similar terms. Don't confuse. One is the alpha s, which is the slenderness reduction factor used in bending. And there is another factor which is called alpha cx, which is used in compression. Okay. So alpha cx, which is your slenderness reduction factor for compression. So you can see that these two are different. This is for bending, yeah. Slenderness reduction factor, you get 0.766. So MSX is given by, MSX is 171 kilonewton meter, already you have calculated. MOA we have got 318.6. MBX is this. You see, this is your alpha M, this is your alpha X, this is your MSX, yeah. So 131 kilonewton meter. Next, we are considering that, you see, once you allow out of plane deformation, then there will be an out of plane bending instead of in plane, out of plane buckling instead of in plane buckling. That means now all the buckling will occur about the minor axis. So lambda ny calculated now, this is 85. And then alpha b equals 0, alpha cy is 0.645. So NCY is given by this. Okay. Correct. So You can compare with this earlier expression. We have calculated NCX, right? Now we have calculated NCY instead, because considering the possibility of buckling about the minor axis. So now we are checking the out of plane capacity. You see now change in terminology. So check the out of plane capacity. 60 divided by 0.9 times 131, and it is 0.9 times 1289. Now you see that both these values have now changed. This is your member capacity considering the, member moment capacity considering the possibility of lateral torsional buckling. This is the member capacity in compression considering out of plane buckling. Now you can see this is higher than 1. So you have to revise that section. Or alternatively, we can calculate the maximum moment and then say, okay, the moment carrying capacity is this much, which is less than the applied moment. So it is inadequate. So have you followed this example? Step by step, first section capacity, then in plane capacity, because we have restrained it not to buckle or bend in the outer plane. And then you have looked at the out of plane capacity. Next, we are looking at the biaxial bending capacity. Now, the biaxial bending, N star is 750 kilonewton, which is the compressive loading. Then M star X and M star Y is provided. Check the section capacity first. You see that section capacity is MSY, this one. And then now we are calculating this. You see this is section capacity, this NS section capacity section we have already calculated, and this we have calculated before. So this is satisfactory. Okay, now let's check the member capacity. Now MCX is the lesser of MIX and MOX. You have to calculate then both of them. MIX is the in plane member moment capacity. You see section capacity and considering the buckling about XX axis. That's why in plane. This is out of plane. So you can actually put a note. This is called in plane. And this is called out of plane. Right? So in plane, you have NCX. And when you go to out of plane, you see MSX becomes MBX and NCX becomes NCY. So the values change according. And you can see the outer moment capacity is given by 46.3 kilonewton meter. So we have calculated both in plane and the out of plane capacity, and then MCX is the lesser of these two. So this is 46.3 kilonewton meter. Obvious. And then we are calculating what is the MIY, which is the, so that means what is the capacity of this section when we are considering the buckling about the Y, and that means minor axis. You see, that's why it is used at MSY. So MSY is 78, and then NCY is 1289. So this is 27.5 kilonewton meter. See this one. When you only consider the in plane one, it was 88. Now we are only considering bending in YY plane, bending and buckling in YY plane. It's 27.5. So much reduction in the capacity. Now we will check the member capacity, M star X over MCX, which is this, and this is your MY star over this one. Now, when there is a, let's look at it this way, this section we have said is subjected to biaxial bending, right? So when there is a moment about Y axis, we will also consider that yes, there is also a possibility of compression about, the compressive buckling about that axis. So there will be a reduction in the capacity. So there's a reduction. So you can see that the capacity has been reduced. Capacity has been reduced for bending, for considering both axis bending, because you see, as I've said, the capacity will be shared. So when we are calculating MOX, we have NCY. Again, when you are calculating MIY, then also there is an NCY. Okay. So once we have calculated this, now we use this expression, which is the basically the interaction formula. It's worth writing. That's an interaction formula. Interaction formula. So the interaction formula, and once you substitute that, you get, see, this is, remember, this is 1 point, I mean, well, you don't have to remember, you're using the expression from the standard, but just be careful that this is, there's a power 1.4 is there. So this is 1.23, which is greater than 1. That means this is unsatisfactory. That means you have to revise the section. Now, if you want to look at the clause number, again, look at this section 8, and this clause number is given by, just hold on. You can write this one. So this is your clause 8.4.5.1. Okay. So that's the capacity of a compression member for the compression member. Now tension member, you have a different clause, the next one. So the section is inadequate. That means you choose a different section and then you move on, or check again whether you can, whether it is satisfied or not. So the key points for beam columns: first, check that each member is okay for the separate actions of bending and compression or tension. Identify all possible failure modes under combined action. This is a very, very important step, because if you miss out anything, no, so then that's a mistake. Check to see each does not occur. Calculations are straightforward but long. Why they are long? Because you have to consider all the possibilities or all possible failure modes. And to remember it in a simple, or understand in a simple way, I will again give that summary. First, you'll start from the section capacity. So if the section capacity fails, choose a different section, revise the section. Once the section capacity is satisfied, you go to the in-plane or out of plane, depending on the requirement. Usually the steps people follow is section capacity, in-plane capacity, and then out of plane capacity, because it is obvious that if you consider out of plane, then you will have the worst capacity or the minimum capacity, isn't it? And then in plane will be a little bit better, because if you consider major axis buckling, it is still better. Why? Because I about that axis is much higher than I about YY. So even that way, it is much more resistive in buckling. But when you consider out of plane, the buckling will be about the worst. At worst means the minor axis YY. So your capacity will be reduced again. Now question time. No question? If there's no question, then I'll stop here.